After publishing my paper, Heaven is the Cause for the Universe Expansion, one of my friends messaged me through Facebook and told me that your theory is rejected by the shell theorem that was proven by Isaac Newton. In this theory, it says that the net gravity on a mass inside a shell would be zero no matter where is it located inside the shell. This theory shocked me and was completely new for me. But after analyzing carefully, I found that there is a great mistake in this theory. The intensity of the gravitational field inside and outside of the shell is proportional to the shell thickness, not to its diameter or surface's area. So as you move away from the shell surface through its center, the intensity of the gravity will not increase due to increase of the surface area, but rather it would decrease due to the distance from the center of mass and gravity. We are familiar with the primary shell where P is located at the center. With no doubt gravity is zero at the center, G equals 0. But what about gravity on P when it is not at the center? According to Isaac Newton, the gravity on P would be zero even if it is not at the center. Suppose that two lines connecting two sides of the shell intersect each other at point P, they will make two head-to-head cones. As P gets closer to one side of the shell and the distance to the center of gravity decreases, the base of the small cone will decrease too, meaning that the amount of the mass pulling on P will decrease. On the other side, as P moves away from the farther side of the shell and the distance to the center of gravity decreases, the base of the big cone will increase. When we calculate the effect of decrease of mass and distance on one side and the increase of mass and distance on the other side, they will cancel out each other, and once again the net force on P would be zero, the same as it was at the center. Before pointing out the mistake in this theory, let's have a review of the center of mass and gravity. Where is the center of mass and gravity of a sphere located, and what is the intensity of its gravitational field proportional to? We know that center of gravity of a sphere is located at its center of mass, the geometrical center of the sphere, and the intensity of the gravitational field of the sphere is proportional to the amount of the mass on the sphere. What would be the gravitational pull on P proportional to? It is dependent to the intensity of gravitational field of the sphere. The bigger the intensity of the field, the stronger would be the gravitational pull on P. Now, what is the intensity of the gravitational field at point P dependent to? It is dependent directly to the mass of the sphere and inversely to the square of the distance from the center. And keep in mind that the direction of the gravitational field of the sphere is directed toward the center of the sphere, meaning that all the gravitational lines are focusing on and pointing toward one point, that is the center of the mass and gravity of the sphere. Now let's consider a shell. Where would be its center of mass and gravity located, and what would be the intensity of its gravitational field dependent to? Remember that center of mass and gravity are always located at the same point, which on a sphere they are located at its geometrical center, but on a shell, center of gravity and mass are not located at the center of geometry. Rather, they are located inside the wall or thickness of the shell, closer to the outer surface than the inner surface. The red line on the above figure shows the center of mass, and we know that the center of gravity is located on the center of mass. So the direction of the gravitational field inside the shell would be from the center toward the surface, and on the outside, the direction of the gravitational field would be from outside toward the center of mass of the sphere, which is again the red line. So the center of gravity on a shell would be an area unlike the sphere, which is a point. Now, what is the intensity of the gravitational field dependent to on outside and inside of the shell? Remember that the gravitational pull on P1 and P2 would be calculated due to their distance from the center of mass of the shell, which is the red line, not the geometrical center of the shell, which is point. So intensity of the gravitational point is dependent to the thickness of the shell, not to its area or diameter. The same would be for the sphere. Suppose the sphere has a shell that its thickness is from the geometrical center to the surface, so as you increase the area of the sphere by adding additional mass, you would increase its thickness, so the intensity of its gravitational field will increase. But for a shell, increase of area by adding addition mass would have two different situations. If you increase area and keep the thickness to be constant, then there won't be any change to the intensity of the gravitational field on outside, because the gravitational field originates from the center of mass and there is no change on it. In the second case, if you increase the area of the shell by adding additional mass and also increase its thickness, then the intensity of the gravitational field will increase because there is a change in the center of mass, meaning that there is more mass pointing toward one point. Now let's come to the inside of the shell. As long as the intensity of the gravitational field is proportional to the thickness of the shell, not to its area, So as you move away from the center of gravity toward the geometrical center of the shell, the intensity of the gravitational field will decrease due to the increase of the distance, but it would not increase due to increase of the surface area or the base of the cone, because as the surface area increases and more mass is covered, on the other side the area of the center of mass or gravity also increases, meaning that these masses are not pointing toward one center, but each individual area has its own center of mass and gravity. So as we move away from the wall of the shell toward its geometrical center, the intensity of gravity does not increase due to increase of the inside surface area, but rather it decreases due to the increase of the distance from the center of mass or gravity, the same as it does on outside of the shell or a sphere. The above figure indicates that increase of the surface area won't have any effect on the intensity of gravitational field, and as normal gravity, it will only be affected by distance. So as we move away from inner surface of the shell toward its geometrical center, the intensity of gravitational field will decrease, and as we reach the central point, the gravitational pull from every direction would be equal, meaning that the net gravitational pull would be zero. But what will happen if we move from the center toward the opposite side? In this case, as we get closer to the left side, the gravitational pull of the left side would increase due to decrease of the distance, and the gravitational pull of the right side would decrease due to increase of the distance. But decrease of the surface area on the left side and its increase on the right side would have no impact on the intensity of the gravitational pull, as we indicated it before. So the central point of the shell is the only point inside a shell where the net gravitational pull is zero, and there is no other point inside it which the net force be zero. Conclusion. Our analysis shows that as the gravitational intensity outside of a shell is dependent to the thickness of the shell, not to its surface area, the same would be inside of the shell. The intensity of gravity inside a shell would be affected by the thickness of the shell, not by its inside surface area. So as we move from the inner surface of the shell toward its geometrical center, the amount of gravitational pull will decrease due to increase of the distance, but increase of the surface area won't have any effect on the intensity of gravity, because each new included area would have its own center of mass and gravity, and as far as they are not focusing toward one point, so their gravitational pulls won't be added to each other and the intensity of the gravity will not increase. And this is the mistake which Isaac Newton had done in his calculations, where he proposed that the new covered areas have a common center of gravity or center of mass. By that way, each individual point or area has an individual center of mass or gravity. So the only point inside a shell with zero net gravitational force would be the geometric central point of shell, and there will be always a gravitational pull toward the wall of the shell and any other point inside it. So the shell theorem is wrong.